Hello everyone, welcome to this video. Let's move on to prove this part D of this given theorem in which we were discussing about operators related to the operator T. So here we wanted to prove these four properties which will further be used in order to prove the spectral properties for the operator T, right? So here we wanted to prove this equation 5, 6, 7 and 8. So let's prove them one by one. So let's have a look at the first equation. So here in this part we wanted to prove that T positive T negative that is equal to the 0 operator and T negative T positive that is also equal to this 0 operator. So that means both of them, they are equal and they are equal to the 0 operator. So we know by definition that what is B? B is the positive square root of this T square, right? So if we square on both sides, so we would obtain B square is equal to T square, right? And moreover from the part B we know B commutes with T, right? Let's have a look how. So we know this B commutes with T, right? So using this thing here for this part, let's see what do we have. So we have B square is equal to T square, one thing, and another thing, this BT is equal to TB. So using both of these things we have T positive T negative that is equal to T negative T positive. This is again using part B. How? Let me show you. This T positive T negative that is equal to T negative T positive, that we have already proved, right? So that this result was there in part B. Okay, so using this result we have using this result B square is equal to T square, BT is equal to TB, and both of them, they are equal to each other. So what do we have? We can apply the definition of T negative, that is half B minus T, and we can apply the definition of T positive, that is half B plus T, right? This is what we have done. Now 1 by 2 and 1 by 2 they club with each other to give 1 by 4, and we can multiply the operators here, B minus T with the operator B plus T. So we have to do it term by term only, and we cannot shuffle the order. So B composed with this B, that would just be B square operator, right? Then B composed with the operator T here, that would be BT and not TB. So that is BT, because we have to keep the order in mind. Next, minus T composed with B, that is minus TB and not BT, right? Because of the order. And then minus T composed with T, that is minus T square. So because you know this T square is nothing but B square, so we can write it like this, and because you know this TB is nothing but BT, so you could write this TB as BT over here. So replacing these terms here, so you see this term and this term cancels with each other, this and this cancels with each other, so overall we have a 0 operator here. So we started with T positive T negative, that was equal to T negative T positive, and both of them, they are now equal to the 0 operator. We have just proved this one. So this proved equation 5 for the part D. Now next move on to equation 6, where we wanted to prove that T positive E, that is equal to ET positive, that is equal to the 0 operator. This is one thing. And another thing, we wanted to prove that T negative of E, that is equal to ET negative, and now that is not equal to 0 operator, but that now it is equal to T negative operator. So we wanted to prove both of these things. So if we take some element X from the given Hilbert space H, then according to definition of this projection operator E, which was some operator which projects whole of the given Hilbert space onto some space Y, which is the null space of the positive operator. This was the definition for E. So it would project, so when you apply this E onto X, which is some element of H here, it would be present in the null space of the operator T positive, right? If that is so, if you, it means when you apply T positive onto this element, you would obtain a 0. So when you apply T positive onto this element, you would obtain a 0, and this is true for every X that is a member of the given Hilbert space, right? This is one thing. Another thing, because we know T positive, that being a combination, linear combination of T and B is self-adjoint. If this is self-adjoint, and moreover we know E T positive of X, that is equal to T positive E of X, right? And T positive of Ex, that is 0, that we already know. So this thing is equal to this thing according, and how E T positive is equal to T positive E, this thing we already know from the previous part, right? We have already proved this thing. So using this result, because this thing is true for every x which is a member of the given Hilbert space, so we have E T positive is equal to T positive E, and that is equal to the 0 operator. So we have proved one part for this equation. For the next part, let's see what do we have. Moreover, we know T positive, T negative of x, that is equal to 0. This we have just proved in the previous part using this thing, right? So according to this thing here, using equation 5, this T positive, T negative of x is equal to 0. If that is so, that means this element is nothing but a member of the null space of T positive operator according to the definition. So this T negative x is a member of this null operator, and because E is a projection which is defined from whole of the Hilbert space to the null space of T positive, so that means it would act as, by the properties of projection, if you remember, this projection E would act as identity if or on all the elements of the null space T n T positive, right? So suppose y is some element of this null space, so E of y would be y whenever y is some member of the null space of T positive. So this is a result. So using this result here, now because T negative x is a member of the null space of T positive, so that means we have E of T negative x is equal to T negative x only, right? So this is one thing, and moreover this T negative is also self-adjoint operator. Why? Because it is again a linear combination of the operator T and B. So using this thing, and part C, that tells us that T negative Ex, that is equal to E T negative x, and that is equal to T negative, right? So from part C we have T negative E is equal to E T negative, right? And E T negative is equal to T negative from here. So you could write T negative Ex is equal to E T negative x, that is equal to T negative x. And this thing is true for every x which is the member of the given Hilbert space. So that means we could talk in operators also, leaving behind this x. So that means we have T negative E, that is equal to E T negative, that is equal to T negative. So this is how we prove the second equation for the second result here for this equation. So until now we have to prove these two equations. Now next move on to the next part, next equation. Here we wanted to prove that Te is equal to minus T negative and Ti minus E is equal to T positive, right? So we wanted to prove these two things. Now again, using the previous results, we know that what is T, that is T positive minus T negative, and equation 6 tell us that we have Te is equal to, so you could write Te as T positive T negative here. So next what you could do, you could open up these brackets. So when you open up these brackets, you have T positive E minus T negative E, and you know what is T positive E from the previous part, it is equal to 0, and what is T negative E, it is equal to T negative. So using these things from the previous part, we have 0 minus T negative, so it is nothing but minus T negative. So that means we obtain Te is as equal to minus T negative here. So this is the proof for the first equation here. For the second result, we consider this thing T I minus E. So let's take this Ti minus E. Let's open up the bracket. So we have T minus Te, right? Now T minus Te. So this thing is equal to T plus T negative. How this is true? Because you know Te is nothing but it is minus T negative from this part here, right? and moreover, so you could write this minus TE as T negative, right, this thing. And moreover, we also know this T is T positive minus T negative according to the definition. So you could write this T plus T negative as T positive. So all in all, we obtain T I minus E as equal to T positive. So using this thing, we obtain the second result for this equation also. So this is the proof for the equation 7. Next, let's see the proof for equation 8. Here we wanted to prove that the operator T positive and T negative, they are both the positive operators. So here, in order to prove this thing, we have to see for some previous results, which are T positive E, that is equal to ET positive, that is equal to the 0 operator, that we already know. T negative E, that is equal to ET negative, that is equal to T negative, that we also already know. B is equal to T positive plus T negative, this is according to the definition that we have defined for T positive and T negative. And moreover, we have also studied this result about positive operators, which tell us that if two bounded self-adjoint and linear operators are given to us and are defined on some Hilbert space, right, such that they are both of them, they are positive, one thing, and they should commute with each other. If that is so, then their product is also a positive operator. So we will be using these results in order to reach at this positivity of T positive operator and T negative operator. So let's see how. So let's first start with T negative operator. So you could write this T negative operator. So using this result here, you could write this T negative operator as ET negative, right? And you could just add a 0 here, no problem in that. Now using the next result, you could write this 0 as ET positive. How? You could write this 0 as ET positive using this result here, right? So from these two results, you could take this E common. So it would be E T negative plus T positive, right? And then what is T negative plus T positive? T negative plus T positive, that is the operator B. So you could just replace it with EB, right? So you have EB here. Now E is a positive operator, being a projection, because every projection, that is a positive operator, and B is also positive operator. Why? Because we have defined it to be the positive square root of the T square operator, right, according to the definition. If both of them, they are positive operator, both of them, because we know EB is equal to BE, they commute with each other and they are bounded as well as self-adjoint. So therefore their product EB is also a positive operator according to the theorem that we have just defined, right? So this EB is a positive operator, and what was EB? EB was nothing but your T negative operator. So all in all, your T negative operator is also a positive operator. So we have proved one part of this equation, that is T negative is a positive operator. Now we wanted to prove T positive is also a positive operator. So for that, we have to again use these kind of results. So we'll be again using these results. So let's see how. So for T positive, what we can do, we could write this T positive from this relation as B minus T negative, right? And again you could write this T negative as ET negative, right? And okay, not this. This time we are writing this T negative from using this equation star. What is this equation star? It is this one. So your T negative is nothing but EB. So we are using this result here, that T negative is equal to EB. So using this result here, so you could write T negative as EB. So that you could take B common from both of these terms. So you have I minus the operator E multiplied with the operator B, right? And now because B, as I have told you, that is a positive operator, I minus E, that is also a positive operator, and because they are self-adjoint and they commute with each other, so therefore using this theorem here, their product is also a positive operator. And if their product is a positive operator, that means what is their product? Their product is nothing but the operator T positive. So that means T positive is also a positive operator, and this is what we wanted to prove here in this last equation for the part T. So I hope you understood this proof here. Well, that is it for this video. Thank you for watching.